request for a problem. Which one was this one? Number 5 in the homework. So this was the 7-3 homework, number 5, and we are asked to differentiate x to the 4th plus 1 times the sech, the hyperbolic secant, of twice the natural log of x. Okay, so we could brute force apply the chain rule, or we could pause and think about what the heck is the sech anyway. So let's see. The secant is what in regular trigonometry? 1 over cosine. So this should be 1 over the hyperbolic cosine. So I just want to pause and think about that. There's my tools. Okay, so that means, just thinking about that right, that's the reciprocal to hyperbolic cosine, which is going to be 2 over e to the x plus e to the negative x, where x here is twice the natural log of x. So then we'll have an e to the negative twice the natural log of x. So that's one way of writing the sech of 2 natural log of x. Now, the reason that looks appealing to me is I see a base e and I see a power natural log, and I know those will cancel if I write them correctly. So perhaps I can get rid of that. What happens to a multiple of a logarithm? What can we do with that? Bring it in as a power, right? Yeah, so this would be then 2 over e to the power natural log of x squared. Highly recommend the use of parentheses, plus e to the natural log of x to the negative 2. And those guys conveniently go away for me, the e and the natural log. So this becomes 2 over x squared plus x to the negative 2. And so then now I can combine that with the other stuff and see if it cleans up any more. So we're not even at a derivative yet. We're just cleaning up the thing we want to take the derivative of, which is always a good idea. So let's see. How am I going to do this? I'll just squeeze it over here. So now I have what? Twice x to the 4th plus 1 over x squared plus x to the negative 2. And I don't know, I'm thinking about multiplying top and bottom by x squared, maybe? Stan, you got an idea? No? Any thoughts? What would you do? Oh, divide everything by x to the 4th? Is that what you're thinking? Okay. Try that. So if we do that, what do we get? We will get that pesky 2 hanging out. Well, maybe. Then up here, if I divide by x to the 4th, I'd have 1 plus x to the negative 4th, or 1 over x to the 4th. And what would we have down here? This would become, let's see, x squared over x to the 4th would be x to the negative 2. Oh, I don't think that's going in a good direction. Plus x to the negative 6. Okay, I don't think I like that. Was that what you had in mind? Or did I do it wrong? Something else you were thinking? Okay, Darren's got an idea. What would you do, Darren? The only way to do that immediately would be to rewrite this as just 1 over x squared, which is one reason I was thinking about multiplying top and bottom by x squared. Might help, might not. So we've got 2 times x to the 4th plus 1 over x squared plus x to the negative 2, and we could just leave it like that and take its derivative. I was thinking about multiplying top and bottom by x squared, and if I do that, I would get 2 times x to the 6th plus x squared over x to the 4th. Oh, no, look at that. Why did I do that? I'm not going to distribute. I'm just going to write it as x to the fourth plus 1 times x squared. I'm going to distribute it to the bottom because that'll give me x to the fourth plus 1, won't it? And that's lovely because now I have a factor of x to the fourth plus 1 on the top and the bottom. So it looks like this is equal to 2x squared. Okay, that seems like miraculous and maybe too good to be true. A couple things I could do to check. Graph that original crazy function, see if it looks like 2x squared. Has anyone done that yet? No? Whip out a graphing utility. I'm going to go grab, where's my graphing calculator? GeoGebra perhaps, or Desmos? I haven't used Desmos much lately. What are you guys finding more useful, GeoGebra or Desmos lately? Your calculator? You have a nice calculator. I'm going to go with Desmos. I think we found Desmos could handle hyperbolic. Okay, so our original function is x raised to the fourth power, then plus 1. And we are multiplying that by the, I think I can just write sech of twice the natural log of x. And that looks a lot like half of 2x squared, right? Okay, why only half? Well, natural log can only handle positive values, so we're only going to get half of them. Another catch there is when I divide by x to the fourth. Oh no, yeah, that's good for everything. Yeah, that's the only catch. X has to be greater than 0, otherwise we're okay. Yeah, okay. So a little algebra saves us from a nightmarish differentiation. So that means we just need the derivative with respect to x of 2x squared, which on a good day I think is 4x. Whew, that was exciting. It's a lot of, well, we worked like half a class the other day for 1. Remember that? Yeah, okay. All right, so we are going to take a quick look at some trig formulas and then we're going to move on to the next section. So where is my calculus book? Math 252, Thomas Calculus, Chapter 7, Section 3. The big thing about Section 3 is there's a ton of formulas that we need. Oh, my mouse is out of control. Blow up. All right. So we got the basic definition of hyperbolic sine and hyperbolic cosine. And those are the main things we need. But what we discovered the other day in class is that there are other hyperbolic trig functions, and the book has their definitions. You can look them up anytime. If you know regular trig functions, then you can always derive the hyperbolic ones. And then it turns out there's all these identities we're familiar with from regular trig, and there's almost the exact same thing exists for hyperbolic trig, like the sine double angle formula. There's a hyperbolic sine double angle formula. There's a hyperbolic cosine double angle formula. Oops, what happened there? So, is there a quicker way to do this? Oh, here we go. On the side, I want these tables. Yeah, so the thing you need to pay most attention to are the tables. So here's a bunch of identities related to hyperbolic sine and cosine, and you needed those to do the homework. The derivatives are pretty straightforward. They're almost just like the derivatives of sine and cosine, with the exception of the hyperbolic cosine is just hyperbolic sine, not the opposite. And then integrals are pretty straightforward. But the biggest thing we got in our tool belt right now are the inverse hyperbolic ones, because they can be written as natural logarithms. Come on, where are you? There we go. This is the most important thing in this section. It's cool that the hyperbolic cosine is the hanging cable problem, but what's more important is we got stuck on trying to integrate things like 1 over 1 plus u squared. We had no way to do it earlier. Substitutions didn't work. But now the fundamental theorem says, hey, the integral of 1 over the square root of 1 plus u squared, well, that's just the inverse hyperbolic sine. Okay. So fundamental theorem combined with these new inverse hyperbolic functions solve a lot of problems we couldn't solve before. They don't solve all of them, but it solves a ton that we were stuck on before. One in particular, I'm a little disappointed that these didn't solve, is a very simple one. Integral of the square root of 1 minus x squared. Does anybody know why that one is so dear to my heart? That's a semicircle, yeah. We still don't have a way to find an antiderivative of a semicircle. The book just says, hey, notice it's a semicircle. So that means if you integrate this thing right here from, let's say, x equals 0 to 1, you've just generated the area of a quarter circle. And we know the radius is 1, so therefore from basic geometry, we know the value, but we still don't have an antiderivative. We will get to that antiderivative in section 8.3, I promise. We're not going to get there today, I'm pretty sure. Okay, what we're going to do today is an idea called integration by parts. In order to do that, you need to remember the multiplication rule, the product rule for derivatives. So can you write down on a piece of paper what you believe the product rule for derivatives to be? No, can you remember it? Think about product rule. What's the derivative with respect to x of something like f of x times g of x? There's different versions of it. Oh, that's supposed to be an x there. I don't know why I put a u. I think I said x. Weird. That's supposed to be an x there. Thank you, Stanton. Okay, so either you're going to write something like it is f prime of x times g of x plus f of x times g prime of x. And some people write it in the other order. They write it as f of x times g prime of x plus f prime of x times g of x. And all that does is change the order of the addition, which doesn't matter. But either one of those. Often we'll write it in a slightly different way. Like we'll let f of x, we'll let u stand for f of x and v stand for g of x. And then we'll write something like the derivative with respect to x of u times v is equal to u times v prime plus u prime times v. All right, so sometimes you see it with u's and v's. F of x, yeah. Okay, so what we're going to do next is integrate that thing right there and see what happens. So we are going to consider the integral of the derivative with respect to x of u times v, and that should be equal to the integral of, let's see, how did I write it over there? I think I wrote it as u times dv dx with respect to x plus the integral of, let's call it v times du dx with respect to x. So here's my u v prime, here's my v u prime. And then we're going to apply the fundamental theorem of calculus to this. What does the fundamental theorem calculus say about the left side? Oops, I forgot my dx here. Just equals u times v, yeah. This is u times v, correct. And on the other side, well, really not much I can do with that because of the product in there. I can't pull out the u because it's a function of x and it has to be stuck inside there. I can't pull out the v, it's stuck inside there. And you kind of sort of can cancel the x's, but they're still there hidden even if you cancel them. So I'm going to leave them in there up there. So I'm just going to rewrite this as the integral of u dv plus the integral of v du. And then just for fun, I'm going to isolate that guy right there. To isolate that guy right there, I subtract the integral of v du to the other side. And so I'm going to change the order a bit and change color. I'm going to say that the integral of u dv is equal to uv minus the integral of v du. In this reversing of the product rule is what we call the integration by parts formula. So basically what it says is if you have an integral and you can recognize part of it as being easily differentiable, that'd be that part, and the other part as being easily integrable, then you can separate them. Okay, you can separate them. So just a simple example of this. Suppose I wanted to integrate x times the sine of x with respect to x. I want to come up with an antiderivative for that. Well, any u substitution I try here, normal u substitution, I got that extra x hanging out in front that's standing in the way of what I want to do. But would you agree that x has a very nice derivative? Yeah. So I would say let's let x be u. Let x equal u or u equal x. And then that means du is equal to just 1 dx. Right? And on the other hand, if I call this part my u, this part right here must be what I'm calling dv. So if I say dv is equal to the sine of x dx, right, and I integrate this sucker here with respect to x, then what I'm going to get is, what's the antiderivative for sine? Negative cosine? It is the negative cosine of x. So I can reverse engineer what v had to be. And usually what you want to go for is u should be something that's easily differentiable and v should be something that's easily integrable. Sometimes it's hard to pick because the sine, differentiate or integrate, it's not that bad. But x, if I integrated it, it gets worse. That would be x squared over 2. Okay, so usually if you pick a u and it looks worse than what you started with, it probably is worse than what you started with and you shouldn't go that direction. All right, so the integration by parts says that the integral of u dv is equal to v times u minus the integral of v du, right? You just switch those guys, essentially. So what do we have here? Then for our black integral, this should be equal to, let's see, what is u here? It is x. V is the negative cosine of x. And then we subtract the integral of v du. V is negative cosine of x. And what is du here? Well, it's just dx, which is nice. And so the hope is after you pull the switcheroo for the integration by parts, your new integral on the other side is easier than what you started with. If that happens, then you're in the right direction. Is that integral easier than what we started with? Definitely, yeah. Now, I didn't write my plus c yet. I'm going to let this guy give me the plus c there. And let's just note we have a positive negative change there. That negative and that subtraction will undo each other. So we're going to have a plus. What's an antiderivative of the cosine? It's just sine, right? Because the derivative of the sine is the cosine. All right, so then here's what I think we have. I think we have that the integral of x sine of x with respect to x is equal to the opposite of x times the cosine of x plus the sine of x plus c. Does that look right from what we wrote down on the other page? I think we have an antiderivative. Now, that was a lot of weird jiggery pokery. We should take the derivative of our result and double check. So just to check, if we take the derivative with respect to x of negative x cosine of x plus the sine of x plus c, what do we get? Well, I have the product rule to use right there. And so that's going to give me, let's see, the derivative of negative x is -1 times the cosine plus, leave the negative x alone, derivative of cosine is negative sine. So I'm being careful with parentheses and signs, and then, or sorry, GNs, plus the derivative of the sine is cosine, and derivative of c is 0, right? All right, how does this clean up? I have a negative cosine plus a cosine, so those add to 0. And then I have a negative x times the negative sine of x, which is x sine of x. So did we indeed find an antiderivative using that crazy rule? We did. So now it's just getting used to the rule and deciding what should be u and what should be dv. And that is the harder part. Okay. So our new magical rule is called integration by parts. If you have something that can be broken into something that's easily differentiable and another part that's easily integrable, then you can rewrite it as u times v. Oops, that was supposed to be a v minus the integral of v du. And so whenever I'm confused about which thing goes where, I think about the product rule and isolating one part of the other side of the product rule, because that's where this comes from. So let's find a more interesting problem to do this on. How about the integral of x squared times the cosine of x? No, let's not do cosine of x. Let's do something a little easier. How about x squared times e to the x dx? So a regular substitution will not work on this one, and that's usually my first thing when I see something complicated. Can I do a regular substitution? And if we tried to do a regular substitution where u is equal to x squared, then we get this extra 2x that I don't know what to do with. But if I go for this region right here, so again, u should be something that's easily differentiable. dv should be something that's easily integrable, meaning you want your derivative to be easier than the function you started with, and you want the integral to be easier than the function you started with. Sometimes it's a toss-up. So let's see, what if I differentiate x squared, I get 2x, that's easier. If I integrate it, I get x cubed over 3, that's harder. So usually if you have a polynomial, that's going to be your u. E to the x, derivative, integral, doesn't matter. Either way, it's the same. So I think the best choice here is u equals x squared. So then du is 2x dx. And I didn't leave myself enough room there. Let's move that. And then I would pick dv to be e to the x dx, because that makes v, integrating both sides there, just e to the x. And so rewriting this, u times v gives me, what, x squared e to the x minus the integral of v du. So I'm going to write that as 2x e to the x dx. And then I always ask myself, is that integral easier than the one I started with? And the answer is yeah, because I got it down to an x instead of an x squared. So I'm better off. But what's the problem here? I can't directly take the antiderivative of that because that x, pesky x, is standing in the way. So guess what we're going to do again? What's that? We're going to do another integration by parts on that. Yeah. So sometimes you have to keep applying it. Okay. So right now we're at the point where we have x squared e to the x minus, I'm going to pull the 2 out, I think, x e to the x dx. Did I copy that correctly? Yeah. And we need to apply an integration by parts to this guy right here, which is kind of like what we did earlier. We're going to let u equal x. So du is equal to 1 dx. And then we'll let dv equal e to the x dx. And so v is again e to the x. Putting that all together, we have our original x squared e to the x hanging out, minus 2 times parentheses, u times v is just x e to the x, minus, always a minus next, the integral of v du, which is just e to the x dx. And now I can find that last antiderivative. I'm going to have to distribute this -2 through, right? So let's see, help me out here. We have x squared e to the x minus 2x e to the x. Negative times a negative is a plus. Antiderivative of e to the x is just e to the x, all of a plus 2 times e to the x. And then positive constant because we don't have integration bounds, because this could be shifted up or down. So notice that we started with a polynomial that was an x squared, and then we ended up with an x to the first and an x to the 0. So guess what would happen if we started off with an x cubed? We would get then an x squared and an x to the first and an x to the 0 and then the positive constant. So the higher the power means you have to keep doing integration by parts again to the leftover piece until finally you get to a point where you don't need it anymore. No, so just to double check here, this x squared e to the x is that one right there. I just brought that down and then switching colors. This part right here is this part right here. Yeah, good question. Yeah, so this is the final answer down there. And, you know, we could factor an e to the x out of these 3 terms and we get a polynomial times e to the x. It's a little less ink, you know, but both are fine. So alternate version of this would be e to the x times parentheses x squared minus 2x plus 2 and then plus the c. So that's an alternate form of this answer. Usually we like to write things simplified, mostly in math. Simplified means use less ink. This uses slightly less ink. All right, let's see if I can find a cute one from the book. By cute, I mean I don't know how to do it when I look at it. It's more exciting that way. All right, so we're skipping 7.4, right? So in chapter 7, we just did 7.1 and 7.3. And I tried to make the homework for chapter 8 relatively small, but it's hard. I think I got them down to 12 to 14 problems each section so far. And I think I edited up to 8.4 right now. Come on, where are you? Chapter 8. There we go. Integration techniques. Okay, so this is another good thing to take a look at. Let's zoom out a bit. We have accumulated a whole bunch of formulas over the last, oops, 2 chapters. Ah, stop it. Where'd you go? There it is. Okay. Yeah, so this is what we know so far based on derivative formulas you guys learned last quarter, and then the new hyperbolic trig functions that we just added here. Okay. And notice we got the square root of a squared minus x squared in the denominator. We don't have it in the numerator yet, which is driving me a little nuts. It's just a semicircle. You think we could find the area of it with calculus, but turns out we need another trick up our sleeves. And we're slowly getting there. So moving on, we have integration by parts. And let's find a cute problem in the homework. Oh, that's a cute one. Yeah, let's try that one. Ooh, that's a cute one too. Example 3 and 4. Yeah, let's do those. There's our formula. Yeah, and notice they show a cute trick here for when you have a polynomial times e to the x, the way the derivatives of the x cubed flow down into that polynomial we generate. Okay. We'll take another look at that tomorrow. I don't have time to look at it again today. So let's look at the integral of the natural log of x with respect to x, because we have not done that yet. Turns out we've integrated 1 over x to get the natural log, but we have not integrated natural log x. So can we do that? That would mean like whatever function this is, so let's call it capital F of x plus c, that means we're trying to find f prime such that the answer is the natural log of x. And although you've done a lot with the natural log of x in these 2 quarters, you have not differentiated a function yet. I'm 96% sure you have not differentiated such a function to get the natural log of x. Okay. So how can I use integration by parts on this? Because there's only really kind of one thing up there. What if let's see, I can't let the natural log be my dv, because that's what I'm trying to do. I'm trying to integrate it, okay? So that means u is going to have to be my natural log. Somebody had their hand up. Was it Darren? Use the inverse function. You know, we could probably, we have a rule for differentiating inverse functions, but we don't have a rule for integrating inverse functions. So I don't know how to use that off the top of my head, but I will look into that. So what's du here? 1 over x, and then let's not forget our dx. All right, so I've used up the natural log, so that means my dv has to be just dx. And if that's the case, let's see, what does v have to be? Just x. Now, okay, so with that in mind, we're going to get that this is equal to u times v. I'm going to write it as x natural log of x minus the integral of v du. Let's see, v is x, du is 1 over x dx. Ooh, isn't that beautiful? This is really just a big happy 1, right? And the antiderivative of 1 on a good day is x. So it looks like this is equal to x times the natural log of x minus x. And then we get that plus c because this is a indefinite integral. Seems too easy. Okay, so I guess to double check, we should differentiate this result and see if it gives us back just the natural log. So we think that an antiderivative for the natural log is x natural log of x minus x. That's an antiderivative if we let c be 0. So we're going to differentiate and see what happens. So new page, check. Oops. Oh well, highlighter check. Not looking so good. Go away. Pen. What happens if we differentiate x natural log of x minus x? Okay, so we got the product rule in the first part. So derivative of x is 1 times the natural log of x. And then we are going to get what, a plus x times the derivative of the natural log, which is 1 over x. This is kind of looking like that UV thing we did a minute ago. Minus the derivative of x there, which is just 1. So that's what, natural log of x plus 1 minus 1. Hey, it worked. It's just the natural log of x in the end. So natural log of x does not have a straightforward antiderivative. It's rather complicated. So just to summarize, the integral of the natural log of x dx is equal to x natural log of x minus x, and then possibly plus a constant. All right, we may have enough time for the next cute problem. Question? Just checking your time. Okay. Next fun one. Integral of e to the x times the, let's do cosine of x, because I think the book did sine of x. So let's be a little bit different. Did I get that right? Book did, it did cosine? Where'd it go? It's up here somewhere. It was example 4. It did cosine. Okay, so we're going to do sine then, because you guys can read the book. You can't read, but you can do calculus. You're a miracle child. All right, so it's kind of a toss-up where to go on this one. We could, e to the x is easily differentiable and integrable. Sine is easily differentiable and integrable. I'm gonna do it in order. Well, eventually, do the one that keeps it positive. Okay, we can try that and see what happens. So you're saying you want the sign to be u, so we don't get any negatives? Yeah. Okay. All right, I wasn't going to do that, but that's fine. Stanton says, let's let u equal the sine of x. I'm always up for a good exploration. And so then du will be the cosine of x, dx. V, or dv, excuse me, is going to be what I didn't pick, which is e to the x dx. So between the u and the dv, you have to account for everything in your integral. V is just e to the x. Rewriting this, what do we get? We get that our original integral is equal to u times v, so e to the x sine of x, minus, so this was u dv, right? U dv, so this has to be v du. So that's going to be v du, e to the x cosine of x. Okay. Am I any better off than I was? I'm actually about the same place that I was before, because there's not much difference between sine and cosine. They're just shifts of each other. All right, so I'm essentially in the same place I was before. However, the alternative was to choose cosine here, which would have put a sine there and a sine here. So, oh no, what are they? Sorry, no, put sine over there, sorry, which put a cosine here. It'll just switch their roles. All right, so what do? Well, we're just going to be consistent. We're going to try doing integration on parts by parts on this and see if something interesting happens. So what do we got? I'm going to go with what Stanton said before. I'm going to let u equal the trig function, cosine of x. So that means du is the negative sine of x dx. And let's see, so then my dv is e to the x, or dx, and v is then e to the x. So we need to recopy the black stuff and my red stuff. So you guys write that down carefully, then I'm going to jump to a new screen. What do you think our whole new line looks like? I'm going to try and write it down. I think we're going to have that our integral of e to the x sine of x dx is equal to, we already found an e to the x sine of x, and then we have a minus my new uv. So I wrote that guy down, I wrote my minus, and then my uv is e to the x cosine of x, okay? E to the x cosine of x, and then another minus, because that's what the rule says. It's going to be uv minus v du. So v du are these guys right here. So that's going to be a negative e to the x sine of x. So integral, and I should have left more space. Can I compact that? Perhaps. Excellent. So now I have in here, I have a negative e to the x sine of x. Oh, dx, just barely fit it. And then I have to close this parenthesis and close that parenthesis. Did I write that correctly based on what we had written down for our red UVs? Double check. UV is e to the x cosine of x. E to the x cosine of x, check. Oops, wrong page. And then v du is negative e to the x sine of x. All right, so we have some SIGNs to clean up and see what happens here. So I'm going to write this in blue underneath and hope it helps. I got e to the x sine of x minus e to the x cosine of x, cosine of x. And then I have a minus, a minus, a minus, right? Which altogether, 3 minuses make a minus. Okay, so now I have a minus integral of e to the x sine of x dx. Oh my gosh, I'm back where I started. No, I'm actually done. Here's why. Check this out. What if we added that sucker right there to the other side? I would have 2 of them. Stanton, you're brilliant. Yes. So if I add that to the other side, then I will have 2 of these crazy integrals of e to the x sine of x dx, and they have to be equal to the other stuff, which I'm going to rewrite as e to the x times the sine of x minus the cosine of x. All I have to do is divide by 2. And I have an antiderivative. So I'll leave it. No, let's switch to, I'll do red. So now I have that the integral of e to the x sine of x dx is equal to e to the x over 2. I'll write it there, right? Divide that over times the sine of x minus the cosine of x. And then technically I got a plus a constant. Can't always assume the constant's 0. I think I've got an antiderivative. Just in time, we only have 20 seconds. Whew. We don't have time to check it. What's that? Yeah, if that was a sine squared and a cosine squared, then that would be the opposite. It wouldn't be the Pythagorean identity because of the minus. It would be the opposite of the cosine double angle. I'm 90% sure about that. Yeah. One thing in this chapter, we're going to get a wicked trig workout in this chapter. In addition to our hyperbolic trig workout. Yeah. All right. So I challenge you later to differentiate that right there and see if it really does give us e to the x sine of x back. I'm 97.5% sure that it will. So according to the schedule that I revised, we're going to spend 2 days on integration by parts. If anybody gets stuck on any of those crazy hyperbolic trig problems, feel free to ask again tomorrow. You're running out of paper. Darren needs more paper. Oh, good question. So those of you listening online, Monday of finals week is now officially a school day. So so our final isn't on Monday now. It was supposed to be. That is now a review day for us. So I got to go check with the Office of Instruction about when this room is free on another day that doesn't conflict with other classes. So you guys will probably have a couple options as to when to take it on like Tuesday or Wednesday.
I'm just going to be out of town. Just going to be busy all day Wednesday.
Yeah, we can. Yeah, I'm sure I can find a room on Tuesday. Yeah. So we'll talk about that again soon.